So that's my the system energies. So this T, this is we call total energy. Of the system. Right? Okay. So that's what we call system energy. Alright. Now what is control energies? If I have a control, say this is my U. My external U. So what is my control energy? Alright, what is my control energy? Anyone tell me what is the control energy? How much energy I have to use for my control? What is my control energy? The control energy we used to use this have the U square, for example. That's what I call here U square. Now, if we have weighted control energies, then I put a weight for that. That's R U squared. Okay. Now, the optimum control is the one that what we want to do is to minimize the system energy plus weighted control energies. For this system, for that only one system, that's one, is not like that. This equation here, this equation will be m w double dot plus k w equal to u. Alright, that's our that is our that's the spring system. But I'm talking about simpler than the spring system. That means x dot equal to ax plus bu. That's a scalar. I don't have a double dot. Alright, for that system, then my system energy I have only state which is x. I don't have x dot to be my state. So that is the so for that simple system, this is more complicated system. If I'm talking about that system, x dot equal to ax plus bu. This is scalar. This is also scalar. Then my total system, I say J equal to the that is half 0 to infinity x square plus r u square, then dt. But by the way, I need to integrate this one too. If I want it to be very accurate, this one has to be integrated from 0 to infinity, and then I need to put a parenthesis here, then dt. Yeah, that's more accurate. Right. If I wanted to know the energies from 0 to infinity, that's infinity. Okay. Now, that's it. Two different systems. One system is this second order system. This is a first order system. This is only a scalar. I'm talking about a scalar here. Scalar here. So this is, I make the problem easier. So that we define is a index called J. That index here called J. And J is nothing but the system energy plus weighted control energies. For this only scalar system, my J equal to half from 0 to infinity, then x squared plus RU squared dt. That's the system. That's the index. Okay? Assume I have J, that's the constant index I define. So we define a cost index. Alright? Now how can I solve this F? How can I solve this control gain? How can I solve this control gain? By giving the cost index. This cost index is defined. I define the cost index. Alright, I define the cost index, and that is from 0 to infinity, and then x squared plus IU squared dt. Alright, now if I sub my x into here, and then you will be able to see that if I sub there, E sub in here, then, well, first of all, I have x equal to there, and then that's, from here is, if you look at this, well, we have to be careful here. Now, x squared is this x squared plus r du squared, and u is fx, so we put fx here first, and then become 1 plus rf squared parenthesis x squared. So u, we sub u from this to there, then we have this x squared. Now, after that, then we have 1 plus rf squared parenthesis sub this xt into there, then we have x squared, x0, then potential 2, because that's a square here, a plus bft and dt. Right? Then we can integrate, because this is all constant, x0 is constant, r constant, f is constant. We assume this f is constant, then have 1 plus f squared, x squared 0, then this is, after we integrate that, we have 2a plus bf, and then e exponential 2a plus bft, then from 0 to infinity. Right? Agree? So you have to understand this formulation first. Any problem? From this step and going to this step, because after that we are going to discuss about this. This is what we are going to do. Any problem about this? Okay? Alright. Now, after that, from here, because we have, what we want to do is we want to try to solve this F. What is F? And how can that F related to our cost index? Alright? Now, cost index. That's my cost index with F here. That's F here. Okay. There's some cases we have to understand now existence conditions. So we have an infinitive here. You have infinity. So we must make sure the cost index exists. How can I make sure this cost index exists? One, assume. We say assume A plus BF less than 0, right? It's not just assume, you have to have that. Because if this not equal to 0, if this not less than 0, then when time going to infinity, that's going to infinity. Agree? So, we have to have A plus BF less than 0. That's required here. I don't care what kind of B I have, what kind of B I have, and A I have. My A plus BF must be less than 0. Because if not less than 0, this cost index won't exist. Agree? Understand? Any problem? No? You agree, right? Keep in mind, because that's I can use this by final exam too. No? What is the exact existence condition for a problem like this? This cannot be larger than 0. Cannot be. Can this equal to 0? Yes, no, no. Because what? Because that equal to 0, then it's going to infinity too. So it has to be less than 0. All right. Let's look at this. You got to be careful here. That existence condition is the key for the cost index to exist. Now, what do we mean? Now, our problem is x dot. Our problem is x dot. Our problem is x dot equal to ax plus bu. Now, a plus bf not less than 0. All right. Now look at this. A larger than 0. That means what? What do we mean for this system if A larger than 0? A larger than 0, what does that mean for that system? That means the system is unstable. Right? Agree? What do you mean A less than 0? This is stable. So, you got to be careful to choose your F, because A less than 0, A larger than 0, they represent different characteristics of the system. Okay? So, the next step, so if we A plus BF less than 0, then our cost index will become like this. Agree? Is that right? If I am satisfied with these existing conditions, my feasible cost index will be like this. Because when